So yeah, so I'll just tell you where I got to. So throughout this talk, the view is going to be finite permutation group acting on the set omega, and H is going to be a point stabilizer. I'm just going to refer to G and H throughout under that assumption. And sorry to begin with the definition, it's a little dry, but I've got to plow through a couple of boring definitions before I can sort of give any examples. Do anything vaguely interesting. So with that setup, if I take some positive integer, typically bigger than 2, and I take a pair of n tuples with entries from omega, then let's call this I, let's call this J, the 2 tuples. Then we're going to say, so we say that I and J are 2 equivalent. And so what I'm going to do for that is write I with a little twiddle and a 2 underneath it, 2 equivalent. If for all I1 and I2 chosen in the 1 up to n, do I use I1 and I2? I use K now, which is probably a bit easier. It's all K now. There exists a GKL contained in G such that I can map the K entry over here to the K entry over here, and likewise for L. Right, so I can just, given this pair of tuples, the corresponding subtuples of length 2, there's an element that maps across. Okay, that's an equivalence relation and what have you. Cool. And then on the other hand, we're going to say that I and J are.
Pick up alpha I distinct. I find alpha K equals alpha.
Yeah, okay. I probably should have K not equal to L.
Oh, no.
Oh, sorry.
No, that's okay. If alpha K equals alpha L and beta K is not equal to beta L, you couldn't do.
Yes, that's true. So it wouldn't be 2 equivalent. It wouldn't be 2 equivalent. Yeah. Yeah. So there is a very good example of you have repeated entries that don't correspond, then you're in a pickle.
Yeah.
So. All right, cool. So, and then we're going to say that I and J are n equivalent. And we're going to write, expect that if there existed G contained in G, and I can map the whole tuple over first tuple to the second tuple. Okay, so cool. And then finally, I'm going to say we call G binary if for all n positive integer n is equal to 2, and for all I and j in omega n, if I've got 2 equivalents, then I've got. Okay, so whenever I can map across in pairs, then that signals that there's some element that can sort of map globally. So it's a bit dull, this definition, but it has nice connections. I'll briefly allude to them. I mean, another way of thinking of it is that in a binary group, if you've got the group acting on the set and you want to look at the orbits of the set acting on n tuples for any n, then you can, all you need to know is what's happening on 2 tuples, and then you can work out all the other orbits. So just knowing the action on pairs will give you information about all the other actions on groups. I know some of you have seen this definition, but some of you probably haven't. So I'm going to just give a couple of examples that are hopefully it's slightly illuminating. So let's take some nice even groups. So if you've got A5 just acting in its normal way. We could let I be 1, 2, 3, 4, and J be say 2, 1, 3, 4. Okay, and I claim, I won't prove it because it's wrong, but I claim that I and J are equivalent, and let's just see an example. What could you see? Yeah. So let's map. Let's look at, say, this pair. This corresponding into the first entry and then the third entry. So that'd be like G13. And so I need to be able to find an element in A5 that can map the 1 to the 2 and fix the 3. So I could just take 1, 2, 4. That's an A5. Okay, and trust me, you can do the same with the pairs. Okay, so I've just checked one pair. And you do likewise for all the others. Wonderful. So that's claim 1, and then claim 2. Oops, claim 2 is that I and J are not 4 equivalent. And why is that? Well, if G satisfies on G being J, then it's probably pretty clear that G would have to just be, you'd have to fix 3 and 4 and 5 because it's not in there. So it just have to be this element 1, 2, which of course isn't in A5. So that means immediately that this action A5 in its natural action is not binary. We found a tuple that's 2 equivalent but not. Okay. Groovy. On the other hand, it turns out that if instead I'd taken S5 in its natural action, that is fine. And I won't go into why, but you can see clearly in this example it'd be fine, right? It'd still be 2 equivalent, but you do now have the element 1, 2, so you're cooking, and it just turns out sort of fiddle about. So S5 is fine in its natural. Really? All right. And that's like the intro. Is that clear? Does everyone get what I'm on about? Cool. So I'm going to sort of stick with this definition because it's easy to work with, and I can say stuff about it. But I should just make some brief remarks, which I'll write in a cryptic form. So the first thing I want to say is there is a nice alternative definition in terms of homogeneous relational structures. Oops. And if you know what they are, brilliant. And if you don't, it doesn't matter one jot. But I mention it because these things are interesting, and so that's a motivation for studying this. And it comes the motivation for the definition comes from model theory, because there are also, to my mind at least, far more mysterious connections to sort of complicated model theory stuff about sporadic structures, stuff like that, which I don't understand. But that's just my way of saying that was interesting, and there are alternative ways of looking at it. I've only given the definition of binary. I should mention that there's we won't really need this definition, but I will briefly allude to it. So there's a notion of a ternary permutation group. As I say, I won't really need it, so I'm not going to define it. But suppose instead of looking at 2 equivalents, I looked at 3 equivalents, whereby I looked at corresponding 3 tuples and seeing if they mapped over. Then I'm sure you could probably, you could follow it all through. Every way you put it, CO2, 3, Bob's your uncle, you've got ternary permutation group, and then obviously more generally with any odd number. And that, if you're doing it with any odd number, you end up with this notion of relational complex. And again, I mention all this a little bit cryptically, just if anyone is interested and wants to do a Google and find out more. But for today, all I'm going to be interested in is binary stuff, right? Groovy, I'm on time. Okay, so that's the end of the intro. I just want to give, all right, 2 little lemmas. I'm not going to prove much really in this Cool, but two little lemmas that hopefully are slightly illuminating. So first lemma is the following, and that is that for any group G, it's not. Right, how did I write this down before? Can't be that hard. Yeah. If G is regular, these are terrible. If G is regular, then it is binary. In other words, if H is trivial. And how do we see this? So proof, let's let alpha 1 up to alpha n be some pair of elements. And we assume that these fellows are two equivalent. Okay, and then I've got to show that they're n equivalent. Okay, so what does true equivalent mean? Well, it means in particular that I've got there exists a G12 such that alpha 1 to the G12 is equal to beta 1, and alpha 2 to the G12 is equal to beta 2. Okay, and similarly, there exists a G23 such that alpha 2 to the G23 is beta 2, and alpha 3 to the G23 is beta 3, and so on and so forth. Right? But it's a regular action, right? So with a regular action, if you take any pair of points, and there's a thing mapping between them, it's the only thing that maps between them. So what does that say? We've got this element here mapping both, mapping alpha 2 to beta 2. Okay, so what does this say? It says that D12 is equal to D23. Okay, so in fact, that element maps the first three things all across. And of course, hopefully you can see how to now extend this. I look at a G34 and it maps the first four things and so on. I'm not going to write the rest of them. But if we end up with D12 equals D23 up to, what was it? Gn minus 1n. And we just call that our G. That map everything across. We'll have INJ being n equivalent. Fabulous. All right, so that's handy. So every single abstract group turns up as a binary permutation group just by considering its statement. That's worth hearing. Oh, this one. Something worse. Okay, never mind. Okay, so the next thing, the second lemma I want to prove is for a particular situation that's going to kind of recur for the rest of the talk. So suppose that H, remember H is my point stabilizer. So suppose that H has the property that any two distinct conjugates of H intersect trivially. Okay, so it's a very restrictive situation, but it can turn out to be one that sort of is a little bit fruitful for finding some nice examples. The formal, sort of, in the literature, that would mean that H is a TI subgroup. For the record. Then what do I want to say? Yes, that's right. So then D is binary if and only if for all H1, H2, H3 distinct conjugates of H. If I do the product of H1 and H2 and I intersect it with the third, H3, then it always turns out to be trivial. Okay, so looks a bit bizarre.
Are you assuming G is transitive?
Yeah, so is that thing? Did I say that at the start?
No.
Oh shoot, did I not? Sorry, that was my
Okay,
mistake. Thank you so much for correcting me. Yeah, I wanted you to be transitive. Oops. Yeah, please put that in. All right. Any other omissions? No, we're all good. Okay, cool. So let me just do a proof of one direction. So what we're going to do, we're going. So let's start over here. So suppose H1, H2, and H3 are distinct conjugates. So yeah, well, I'm going to prove that if yeah, so I'm going to prove that if I don't have this property, then G is not binary. Okay, so that's the directional. Suppose these are 8 distinct conjugates of H, stabilizing alpha 1, alpha 2, alpha 3, and omega respectively. And then let's assume that there exists a non-trivial element H that's inside this fellow here. Okay. Wonderful. And then what I'm going to do is I'm going to let I be alpha 1, alpha 2, alpha 3. And I'm going to let J be alpha 1 for the H, alpha 2.
That condition isn't H1 times H2 in second H3 or
Yeah, so do this product first. Does that make sense? Yeah, do the product, then do the check the intersection. Okay, and what I'm going to do is and what I'm claiming is that well, let me do it in 2 stages. So first, I claim that I and J are not 3 equivalent. Okay, why is that? Maybe rather than writing it, I'll just sort of state it. So the first thing to note is that this alpha 1 and this alpha 1H really are different. Okay, because H is inside H3, so it's not inside H1. So it's definitely moving. It's definitely moving the alpha 1. Does that make sense? Yeah. So these two tuples are different. Now, if I wanted to map this all the way over to here, in the first instance, I'd need to map both alpha 2 to alpha 2 and alpha 3 to alpha. So I'd have to fix both alpha 2 and alpha 3. So I'd have to be in both H2 and H3. But they intersect trivially by assumption. Does that make sense? So the only thing that fixes both of these is the identity, but of course the identity doesn't say that to that because they're different. Is that all right? I can write it down, but I'll probably make a mess of it. Good. So that's good. So now if I can show that these are 2 equivalent, then I'll be done, right? Because I'll have said, well, if this is not true, then this is not true. I'll have found something that is they're 2 equivalent, but they're not 3. Okay. So let's just see this little sort of very quickly. So let's write H as H1 times H2. H1, and H2, H2. And why can I do that? Because I'm in this product. Okay. And then I've just got to check the pairs. Okay, so if I want to map, the first thing I want to do is map alpha 1, alpha 2 to alpha 1H, alpha 2. And I think to do that, all I need to do, I just need to do an alpha, I don't need to do an H2, right? So if I just map the H2 across, then that will fix the alpha 2 because H2's inside there, and it does the same thing to alpha 1 as H does. okay, because it's equal to that. And then similarly, alpha 1, alpha 3, I want to map that to alpha 1, H, alpha 3. Then I think all I have to do in this case is use what am I doing? H1. H, sorry, excuse me. Yeah. Yes, fine, thank you. And then finally, I need to map alpha 2, alpha 3. I can do this one. So alpha 2, alpha 3 with an identity. All right. So I found that. So what did this tell me? This tells me so D is not binary. I'll prove one direction. I'm not going to bother with the other. All right. Splendid. All right. So that's my lemmas. So I now want to focus in on a specific situation. So I'm going to assume, sort of, there's a moment when I'm going to not quite assume this, but for most of the rest of the talk, I'm going to assume that G is simple. So this is G as an abstract group. So what I'm interested in, the question I sort of wanted to answer was, if I take any simple group, what binary actions could I possibly find? So yeah, maybe I should write this. What binary actions does G have? Question mark. Well, so one answer is obviously the regular action group B. So apart from that, what else might I be able to find? And sorry, by implication, I mean transitive. Given I've already missed that out once, maybe I should just be very clear. Binary transitive action, just to make life a little bit easier. So yeah, I've got the regular action. Now it turns out, so it seems that such actions, other non-regular binary actions are rare. And I mean that not in a technical sense. What I mean is I can't find many. So and this is perhaps a little surprising because so here's a fact that if you've got G simple and if you've got H of prime order, then the action of G on cosets of H, how we want to write this, write it like that, is either binary or ternary. This is, I'm not going to bother proving this, it's quite an easy fact. So it's either defined by its action on 2 tuples or its action on 3 tuples. And I mean, to me at least, like the difference in 2 and 3 isn't much. And so I'd be like, half of them are probably binary and half of them are ternary or something in my ignorance. But what it seems to, and obviously, simple groups have lots of these sorts of subgroups, so you think there's going to be blooming loads of them. But what seems to be the case is actually, no, not so much. Those ones are almost always ternary, and just very occasionally you might have a binary one turning up by sort of random happy thing. So let's have a look at what we might get. One other thing I should make a remark on is the fact there are no primitive binary actions. So this might be the first bit for G simple. That might be the first question you want to ask. And that's a result of this sort of thing that me and Martin and Pablo and various other people worked on. And so we can rule that out. So where else? So where to look next? This is really the question that sort of started me off. So I want to spend the rest of the time just showing you some ones that I have found and speculating idly about what might be the case in here. So we're continuing on this assumption G is simple. So the first particular case I want to look at is G being PSL2Q and H being non-trivial and cyclic. Okay. So what I wanted to do was exploit this lemma here, because in this case, when G is PSL2Q and you've got a non-trivial cyclic subgroup, it's a TI subgroup. This is just a I don't know, consequence of all manner of things, but it's you can easily see that. Okay, so on the face of it, then it seems like this is a good thing to look at. And I was kind of interested. Also, I was thinking like, so you're interested in this property of these things intersecting. This, so you've got a product of two things intersecting third thing. And that kind of reminded me of these theorems about products of conjugacy classes. So I wanted to sort of exploit that. And so the theorem that I want to use, which I found is in a paper of Garian. She proves like loads and loads of stuff in there, and this is just a tiny special case which may well have already been known. But anyway, I'm going to credit it to her. So let's C be a conjugacy class of PSL2Q with Q at least 4. Then the product of C with itself contains C. Yeah, like I say, she proves loads more. She like spells out exactly, exactly if you've got a conjugacy class, what are the conjugacy classes it contains. But for my purposes, this is all I need. Because you can probably, I'm not going to spell out the proof. I'm just going to say this, the thing that we were able to prove with it. Oh, and I should just say, actually, all of this stuff, sorry, I'm not giving credit, is with Pierre Guillaume. All this stuff on simple groups. Sorry. Okay, so here's what we looked at that, and we were interested in trying to exploit this theorem here, this lemma, and so we proved the following. So let H1, H2, H3. Sorry. One of the following. One of the following occurs. So there exists H1, H2, H3, distinct conjugates of H. Such that H1 times H2 in section H3 is not equal to the identity. Okay, so that means it's not a binding action. And in fact, I think we can be more. I think actually what you can assert is that H3 the whole of H3 would be contained in here, but I'll write that to be cautious. Or the other possibility is Q equals 2 to the A with A odd and H equals 3. Oops. And these are mutually exclusive. So the second case really is different. So you can probably imagine how this might go. But I'll just make just a brief statement. Why is H equal to 3 important? So the point is, so I mean, why if you take an element of order 3, two elements of order 3 inside PSL2Q, and you this tells me that if I multiply them together, it's possible to find two. So if I multiply them together, I get a third one. But what actually happens is that actually the only way that happens is if the one you took at the start were actually equal to each other. So you get G times G, and then you get G squared, and that's also an element of order 3. And nothing else happens. And so if you then look at the subgroups, you don't get these distinct conjugates because H1 is actually equal to H2. That's all. So it's a little bit blathery, but I hope you can imagine. Whereas for all other cases, in order to get two things multiply, like say you've got an element of order 5 and another element of order 5, and you want to multiply them to get an element of order 5, they really they can't be powers of each other. If that makes sense. So you really end up with distinct. I hope that sort of makes sense. Cool. Okay, and so what does this mean? Oops. Probably that G is binary under this assumption, right? So G is binary if and only if it's using the PSL, SL2 is the A odd. It seems a bit random, but so we go. And initially, when I saw this, because my long-term aim is like it'd be nice to know what they all are, and I saw this example, I was a bit like, God, maybe there's these all sorts of weird things sculling around. It'd be hard to sort of figure out what's going on. But hopefully we shall see. I think maybe there might be a little hope to say something. All right, so I'm just going to leave that for now. The next example I want to consider is G be SL2Q, and let H be a still P subgroup of G. And just to be clear, I'm talking about P being the characteristic. And I know SL2Q isn't always simple, so this is the bit where I slightly diverge from that assumption. Although, importantly, when Q's a pair of 2, it is simple, so we're all good there. And what I claim here in this case is that D is binary. So in the action on cosets of a Syloff P subgroup, you do have binary action. And I'm going to think of this action as the action on cosets of that Syloff P subgroup. But it's also worth saying what that action is. What an action we all know and love. It's just the action on non-trivial vectors, vector space. So there is a geometric way of proving it as well. I'll just go with this. So how would I prove this? Well, the first thing to note is that H is the TI subgroup. Okay, so distinct conjugates of Syloff P subgroups in SL2Q intersect trivially. That's probably a familiar fact, but if not, something like that. Secondly, G acts two transitively on conjugates of H. And that means that I'm at liberty to choose my, if I'm so now, because of this TI subgroup thing, I'm going to be looking at this condition up here. And so I'm at liberty to choose H1 and H2 to be my very favorite Syloff P subgroup. So here, with no further ado, here my very favorite Syloff P subgroup. H1 is going to be, do I go lower or upper first? So it's all the things that look like that. And then H2 is going to be all the things that look like that. And then what does that mean? I multiply them together. I'm going to be bold and attempt to do this in front of you. Let's see how we go. So we've got 1 plus AB. We've got an A. We've got a B. We've got a 1. I'm okay. Good. Good. And then I want to check, I'd like to show, so for, I'd like to show that this H1 times H2 contains, what do I want to say here? No P elements apart from those in H1 and H2 themselves. Does that make sense? Yeah. All right, but in SL2Q, so if G is in SL2Q, then G is a P element, implies, just by messing around with trace of G is equal to 2. Okay. And so what does this mean? Well, the trace here is 2 plus AB, right? So if there's a P element in H1, H2, then it's equal to a product of things looking like this. And we need 2 plus AB to be equal to 2. Sorry to write this down in shorthand, but hopefully it's clear. And obviously A or B is going to be 0. If one of them is 0, then the product you end up with is in whichever. Does that make sense? Okay, cool. Wonderful. So that's groovy. So we've got that's a nicer example. I like that one. Firstly, because it's got a nice geometrical interpretation, and thirdly, because it seems like there's some hope of thinking about using this as insight for groups of higher rank. So that's what I want to do for the remainder. Are we all good? Is there any questions? No? All right. So my final scenario that I want to consider is that G is a simple group of Lie type. And I'll write G as GQ, which sort of quite often is the size of the field that it's defined over, just occasionally not near enough. And I'll also assume that H is the center of a long root group. Now, if you're unfamiliar with this, in a sense, it doesn't really matter. You can just say this is just some limit group in the end. But and probably most of you know this more about this than I do. It's not hard. So let me just give you an example. So if you use SL4Q, then here's a nice example of a root subgroup. It's anything with just one. It's a set of Q matrices where the only non-zero off-diagonal thing is just in a particular place. Okay, and then all conjugates of that little beast. So in that, all conjugates of that would include all the other places that you can put these, but also those ones. Okay. Cool. And so, and in SL4Q, so this is abelian of order Q. So this center bit is neither here nor there. You need to specify a center for this, what I'm about to show you, to work for twisted groups, because in that case the long root group might be abelian. But think of that for now. That's good enough. And so I'll just note that H is always of size Q, as it turns out, and also that H is Ti. This is just due to some stuff that you can find. All right, and now I want to state a theorem that. And again, I'm sure you can imagine. Oh shit, I've deleted it. Anyway, you know the lemma that I had up there with the h1 times. That's what I want to use. So I want to. Is it? Oh no, that's where I used it. The original one is deleted. Anyway, that's what I want to use. So I'm gonna try and find. What I'm going to show, hopefully, is that sometimes, at least, for certain choices of G, when you take H to be this fellow here, you do get a binary action. And so because H is a TI subgroup, what that amounts to is checking this product intersection condition, which I initially was absolutely baffled by, and then stumbled across this theorem. So that's to give due credit to Google for this little fella. It's a theorem that I do not know who to ascribe credit to. So I'm just going to write loads of names down. So there's something like this appears in a paper of Achbacher and Sykes, which is the one on involutions in Chevrolet groups. Then Cantor states it without proof and with some rather cryptic remarks, which may or may not set shit light. And then Cooperstein has also written some stuff about it and got probably loads of other people as well. So here's the thing. So let G be any finite simple group of Lie type. And let H be the center of the. Oh, sorry. Excuse me. Of rank at least 2 and not 2 and 4. Let H be the center of a long root group. And let H1, H2 be distinct conjugate. Of H. Then one of the following happens. So this is blooming amazing. We know exactly what might turn out. So the first one is that H1 and H2 are elementary abelian. And what is more, and so what's key, of course, is that this thing generated by H1, H2 in particular contains H1 times H2, right? So everything I'm going to say is going to be about this group that H1 and H2 generate. And so given I'm just interested in studying the product, I can just work inside there. So if I know what this fellow looks like, then I can forget my big complicated group of Lie type and just work in that super easy group here. Okay, so the first case is H1 and H2 are elementary abelian, and every element of this H1, H2 is a long root element. So by long root element, I mean just an element that turns up in a conjugate of H. Okay, so it turns up in a conjugate of H. So just to see, so we can all see this really transparently, let me give an example here. So if I was to take my H1 to be everything that looks like that fellow there, so this is supposed to be row 1 in column 2, and then my H2 to be everything that looks like, clear, row 1 in column, so row 1 in column 3 now, then the thing they generate would be pretty clearly just everything with entries either there or there, both, right? And it's pretty clear that anything, if you've got just non-zero entries here and here, then it's conjugate to and things with just entries here. So they're all long groups. Does that make sense? Sort of waving around. Okay, cool. Second is that, same again, they're elementary abelian, but this time the only long root elements are in H1 union H2. Okay. So an example over here would be if you have one, the same H1 that you had before, but this one now, you thing down here in the bottom corner, okay? Because these clearly commute. But and again, what do they generate? Things that just have entries either here or in both. But if you've got non-zero entries in both, your Jordan form's different, right? You've got 2 Jordan blocks. size 2. Whereas if you've got entry just in 1, you've got a Jordan block of size 2 and then 2 of size 1. So they can't possibly be conjugate to each other. Okay. So that means if you've got your long root elements, that the only long root elements are the ones with these Jordan blocks size 2, just a single Jordan block size 2. So they must be open union. H1 H2 is equal to, or is isomorphic to the Syllop P subgroup of GL3 or SL3, whichever. Yeah, GL3Q. And I don't know what's a bit boring this, but H1, what do I want to say here? H1 and the center of this fellow are of type F1. So what do I mean by this? I mean, if you take the two root subgroups, you can generate the upper triangle as size 3, and lying inside it, you have a cheeky copy of this first thing here. And the way to see that, in this case, would be 1 right here, and then you've got, where is it there? You can see clearly that it's at the bottom, but it's not relevant. These two things are just going to generate all your upper triangulars in here of size 3. And in particular, if you've generated all of these fellows up here with these two beasties, then you've got this inside it, right? And this one here is going to be the center of the thing you generate. Sorry to be rushing a little bit, I'm slightly around. And finally, H1 or H2 is isomorphic to SL2G or PSL2G. The G is the only form. And that's just if they're opposite. It's probably from 1, 1, 1, 1. That would just the SL2's in the top left. Cool. And that's it. Those are the only things that can occur. Brilliant. So what was I'm going to run out these because I need to write some stuff down. So now I've got these 4 possibilities. I'm interested in my H1, H2, H3 condition. So the thing to note is if suppose this F1 occurs, right? Suppose F1 occurs, then what this is saying is if I take my H1 and H2 to be like they were before, then I can find an H3 that intersects their product. Non-trivial. Actually lies wholly inside of H1, H2, but whatever. Okay, because everything inside that product is a long root term. Okay. But on the other hand, here, if I take an H3 and try and intersect it, it's only going to intersect H1 and H2 themselves. Okay, so it's and their trivial intersection subgroups that can't occur. So this is that there does not exist a block. Does that make sense? So I realise I'm going a little hurried, but hopefully this is making sense. And then F3 is another there exists. Why? Because well, it can if you've got an F3, then by implication you've got an F1. You could have just taken the other two H1 and H2, one being the centre. Okay, so that's there exists when they're not like that. And then finally this one. Well, we actually just proved this, right? We proved that if you've got, so in this case, you've got Syllop P subgroups inside an SL2, and the thing that I just proved was if you've got Syllop 2 subgroups inside of an SL2, then it's a binary action. And so there do not exist these things, because that would be precisely the condition that I just proved in the previous board. Okay? So just to remind you, this is the condition which means if they don't exist, then this is the condition that allows us to say, ooh, we might have some binary action. But as soon as you've got something like this, then you're dead. Okay. And so in particular, of course, in SL4, you're dead. Like we saw in SL4, all 4 of these things can occur, right? So you can get this condition and this condition as it happens. And so immediately you're dead. You can't have a binary action because you can find a triple with this non-trivial intersection. So SL4 is not going to work. But now, sort of denouement is that So fact, it turns out, oh, well maybe before I say the fact, so let me just sort of corollary. The action of G on this coset of H is going to be binary if and only if only F2 and or F4. Okay, as soon as I've got an F1 and F3.
Your theorem is stated for the finite simple groups.
Yeah.
It's the original simple. So you well.
Oh, sorry. Yeah.
To the center axis.
You could do, yeah. Yeah, sorry, you're quite right. I've sort of just brushed over it, but you're right. That means I can state it for quasi-simple. Okay, so and now here's a fact that there are groups. What do I want to say here? Okay, if G, so let's go back to this here. Let G be finite simple group of Lie type of rank, and let's greater than equal to 2 and not 2F4. Then only let H be the blah 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 same again. So only F2 and or F4 occur if and only if, and this is sort of known stuff from the literature. G is either PSU into or PST. And so we have binary actions in those two cases, but not in the others. Okay. And so, to my knowledge, those are the first binary actions we know of with unbounded rank, not non-regular binary actions. So that's a nice fact. And then I've ruled out the rank 1. So I'll just note that so if G is it, even though this theorem doesn't apply, you can still have the same setup in rank 1. So if G is 2B2, 2D2, or PSU3, the action is binary. Same proof, you just have to fiddle about more. You don't get to just quote massive theorems from other people. And then if G is SL2, PSL2, then G is binary. PSL2 binary if and only use even.
So that's more general than your other examples.
Sorry, which?
So your other example is L2 becoming A.
Oh yes, yeah. So that's right. So when H was size 3, you're absolutely right. So when H is at size 3, you need Q to be 2 to the A they are, but this always works. Yeah. And then finally, G is 2 and 4. I don't know what the answer is, but that's because I haven't. I don't think it's well. I could. It might be hard. It might not be.
We need to extract some small primes for the percentage position.
So where you? Oh.
Yeah. And,
Yeah. Okay. So you're right. I'm assuming G is simple. So yes. Yeah, so exclude. Yeah. Yeah. Exactly. Yeah. But actually, that does remind me though. One interesting fact. So 2G23 is a good thing to just muse upon. So 2G23 is not included in this statement because I'm assuming that G is simple. But 2G23 prime, if you remember, is no more or less than FL2A. Okay, and you can talk about long root subgroups in that scenario. And the center of a long root subgroup is, wait for it, a cyclic group of order 3. So even though those C3s look like they're a totally different phenomenon, at least for the L, so remember SL28, it's 2 to the 3 and 3 odd. So this turns up. So in that case, even though it looks totally different, it is actually just the same thing, 2G2. Of course, then once you get to 32 and whatever it is, I don't know what's going to just happen to be there. But that kind of pleased me. So there we go. So we've got a whole bunch of nice examples. And now let me conclude with a bold and probably totally unjustified conjecture. But the conjecture is basically that I've shown you all the examples. I've got no idea whether that's true, apart from the fact that I've tried really hard to find other ones, and I haven't been able to. But for the record, let me state it. So conjecture. So let's let G be simple. Let's let H be a proper subgroup of G, and G act on cosets of H, same cosets of H. So this actually is binary. If this actually is binary, then you want of the following. H could be trivial. G could be SL2 to the A odd. H of size 3. Or 3. G could be isomorphic to a group of any type, for which H is a long root subgroup. Oh, sorry, center of a long root. And that would incorporate all the examples. I haven't stated it as an if and only if because it's palaver to just write down exactly what occurs here, but effectively it's an if and only. And actually, it's not far, although it's stated in terms of the transitive actions, it's really a statement about all actions, because for some reasons that I didn't go into. Once you know the transitive actions, you can sort of pick out which ones, the intransitive ones as well. So this would complete the picture for simple groups. So I'll just say that it's known to be true, but not very many cases. But it's known that if G is equal to PSL2Q, so this is work I did with PAPO. And then we've a bunch of things with the old computer. So for instance, the Mathieu groups. So this is saying the sporadic groups, only turn up with regular action. So we've run code on Mathieu groups and so. All right. Thanks.
Am I right in thinking that in all the examples, H is a TI subgroup?
Yeah.
That's no.
It's not a condition, no.
No.
Yeah, in principle, you could have
Yeah.
Other binary actions. It just
seems like
that's the way. I mean, yeah, but if there was some nice way of somehow using the simplicity of G to show binary action necessitated the stabilizer being TI, that would be, wonderful. But
if you had a counterexample, and if your point stabilizer contained these guys, would you prove that the lifted action?
oh yeah, well, so it's binary actions don't behave really badly on all sorts of subgroup inclusion-y things. So the only thing, I'm not sure if I'm exactly answering your question. So, but if you've got a suppose you've got this setup here, H inside an M inside a G, and suppose your G acting on cosets of H is binary. Then one very, very useful thing that is true is that M acting on cosets of A is binary. So that is true. But G acting on M isn't.
So what my question was, if for example, the assume G actually and binary, would you know anything about G?
No, I don't think so. No, I think you're in the right topic. Yeah, yes. So it's quite badly behaved.
I guess that this result extends with sure extension, so this kind of perfect extension.
Yeah. So you would say if I was just talking about quasi-simple instead of simple, is that what you're saying?
Yes.
Yeah. So okay. So I was thinking of presenting the previous stuff in terms of quasi-simples, but I'm just a bit. There's some of the literature I find a bit hard to read on the whole root subgroup stuff. I think it's true, or everything works in the quasi-simples, but I'm just a bit too ignorant to be sure. But I think the short answer is yes. That for quasi-simples it should be the same sort of story. But yeah, I'm just a little more nervous about saying.